Hi there, welcome to another video from Hegarty Maths. It's Mr. Hegarty here, our fifth video on Venn diagrams for probability. Let's start with something I need you really familiar with for this video, and it is labeling regions on Venn diagrams. Pause the video and double check you can name each of the shaded regions in the 9 pictures below. Well, hopefully you got the following answers. If you were struggling with that, do go back to the section on set theory, which is in the building blocks. Now, not only can you use Venn diagrams to count sets, you can put probabilities and count probabilities within Venn diagrams. So for example, I could assign probabilities to each of the regions in the diagram. So let's see what regions we have. We have got the region A intersect B, we've got the region of A not B, the region of B not A, and obviously the region outside that's neither A nor B. They obviously must all add to 1. And I've done that in each scenario. Use the diagram shown to work out the various probabilities in question. Well, it's just adding up really. The probability of A is everything in the shaded, 0.2 add 0.1 is 0.3. Okay, the probability of not A, everything shaded, 0.4 add 0.3 is 0.7. Probability of B, 0.1 add 0.4, 0.5. The probability of not B is everything in the shaded, 0.2 add 0.3, which is 0.5. The probability of A or B, it's everything that's in A but not B, in A and B, in B and not A. So 0.2 add 0.1 add 0.4, which is 0.7. The probability of the complement of A or B, or not in A or B, is just the 0.3 here, everything outside the two circles. Probability of A intersection B is this overlap here, which is simply 0.1. The probability of A intersection not B, well, in this particular case it is just the 0.2. That means everything in A but not in B. And the probability of not A intersect B, i.e. everything in B not A, is just the 0.4 here. Right, another idea I need you familiar with. Do you remember what it means for two events A and B to be mutually exclusive? Well, hopefully you remembered that it's mutually exclusive if there is no overlap between A and B, but the mathematical way of saying it really is that the probability of A intersection B is 0. There is no probability of A and B happening at the same time, and that idea we're going to use a lot. Now the last thing is a result I'm going to prove for you. I haven't used it before because you can answer most questions without it, but I think it's a useful result and could make solving some of our problems much quicker, and this is it. It says for any two events A and B, the probability of A or B is the probability of A add the probability of B, subtract the probability of A intersection B. Now it's fairly common sense, and I do want to prove to you why it is true. So I've drawn a picture here in the scenario where A and B are not mutually exclusive. I'll show it's true in that scenario, and I'll show it's true if they were mutually exclusive. Now let's think to ourselves. Everything inside the circle for A means the probability of A. Everything inside the circle for B is the probability of B. Everything in this overlap here is going to be what we call the probability of A and B. Right? Now, the probability of A or B is everything in this bright red region, everything in the overlap, everything in this brighter blue region. So in these three regions added up. So let's give a label to this bright red region. We can't just write that's the probability of A. It isn't. It's what's left over after you take out the probability of A and B. So we would say this is the probability of A, subtract the probability of A intersection B. And similarly over this side, this brighter blue region here is everything in the circle probability of B, but take out this intersection, probability of A and B. Now we know if we add this, if we add this, and if we add this, it will give us the probability of A or B. That is what the probability of A or B means. So the probability of A or B is going to be this at this at this, which we can write down. Doing a bit of collecting like terms, that just combined to subtract negative A and B, and tidying this up, we get our result. Now, in the case that they were mutually exclusive, so they had no overlap, it obviously does still work, because when they're mutually exclusive, the one fact you know for sure is the probability of A and B is 0. So the probability of A or B, in this case, is clearly what's the red region, probability of A, plus what's the blue region, and we're done. And it's also, you could think of it as taking away the probability of A intersection B, but in this case that is 0, so it doesn't impact. So this formula works in that scenario too, so the formula works in any scenario. Okay, That's virtually it. The only other thing I would say is sometimes you want to rearrange this formula. Sometimes you want that the subject of the formula. So you would write it as probability of A intersection B is the probability of A plus the probability of B, subtract the probability of A or B. And I need you to commit both of these two results to memory and to be able to use them at will to make questions easier. So here's the first question. Pause and have a go. So we've got A and B are mutually exclusive. It gives us the probability of A and the probability of B. I find it always easier to do these questions by drawing a fully labelled Venn diagram before I even think about the questions that I'm given, because usually then it makes these questions rather trivial. So let's have a general Venn diagram. Can you think why that one isn't quite appropriate? Well, in this question, we are told that they are mutually exclusive, so they must have no intersection or no overlap. So I should have drawn the diagram like that. So why don't I label this A and this one B like that? The probability of A we can put inside this circle is a third. The probability of B we can put inside this circle is a fifth. Now the other region we should label the probability with or assign a probability to is everything outside A or B. Now how do we work that out? Well, everything inside this must add up to 1. So to work this one out, we would do 1 everything here, subtract the answer to a third add a fifth. These two combine together. Now a third add a fifth is going to equal, if you work that out, make them both over 15, so it would be 5/15 add 3/15, which is going to be 8/15, and 1 subtract 8/15 is 7/15. So this here is 7/15, like that. Now we should have everything we need to answer these questions. What's the probability of A intersection B? They're mutually exclusive, so that's 0. They have no overlap. What's the probability of A or B? Well, it's everything in A, add everything in B. We've already worked out a third plus a fifth here. We already worked that out as 8/15. So we can, because we've done all the hard graft earlier on, we can just write that down as follows. The probability of the complement of A or B, everything outside A or B. Well, again, because we've done the hard graft earlier on, it's simply 7/15. Or you could have done it by doing 1 subtract this. Now, what's the probability of A intersection not B? So everything that's in A but not in B. Everything that's in A but not in B, in this particular case, is just everything in A because they have no overlap. So that's just going to be a third. And similarly, the probability of not A intersection B, everything in B but not A, is just in this case everything in B because they have no overlap. And the last thing, the probability of not A intersection not B. So everything, you think of everything not in A, and where is that the same as everything not in B? Well, it's outside A or B, it's the 7/15. Now there's something I wanted to point out to you before we move on to the next question. It always turns out that the complement of A or B, the probability of not A or B, is the same thing as the probability of not A and not B, intersection not B, like that. They always turn out to be the same thing. Last question, pause the video, have a go. Right, in this case we're given the probability of A and B and the probability of A intersection B, so we know they're not mutually exclusive. Let's draw a Venn diagram. I always find it handy, as I said before, to fully label this up before I answer the question. So let's see what we can label up. This here is the most important fact, which we can put in first of all. So we can say that is 1/20th, label that A, label that B. What would we put in this region here? Well, we would say it is everything in A, which is 2/5, subtract the overlap, which is 1/20th. Okay, make that both over 20, multiply this one by 4 top and bottom, that's 8/20th, subtract 1/20th, which is 7/20th. So we can put that in there. We can work out what should go in here by doing everything in B, which is a quarter, subtract 1/20th, making over the same common denominator. You get 4/20th, and that simplifies to a fifth. So up here I'm going to write 4/20th to make calculations easier in future, but also write in a fifth. The only other thing we should label is what goes outside here. Well, all these must add up to 1. So 7/20th, add 1/20th is 8/20th, add 4/20th is 12/20th. So this region must be 1 subtract 12/20th, which is going to be 8/20th, which simplifies. I'm going to write 8/20th, and I'm also going to write the simplified version as 2/5 there. Now we've got everything we need to answer any question in this case. Now, we could use the result for the first one. Probability of A or B is the probability of A, add the probability of B, subtract the probability of A intersect B. That's a result we know, and I introduced at the start of the video. Add that, and take away that, you would get the right answer. But because of all the graft we've done, we could just add 7/20ths, 1/20th, and 4/20th, which would give us 12/20ths, and 12/20ths simplifies to 3/5, and we'd be done. But you could have used the result I showed you earlier. Now, continuing, the probability of the complement of A or B, that's everything outside the two circles, which we've done the hard graph for, is simply 2/5. The probability of A intersection not B, so everything in A not in B, we've done the hard graph, it's simply 7/20ths. The probability of not A intersection B, everything in B not in A, again we've done the hard graft, and it was 1/5. And lastly, the probability of not A intersection not B, again we've done the hard graph, it's this outside region, and the answer is 2/5. And that's it for this video. Thanks loads for watching.